Okay, let's continue talking about esterification. Besides being just like a really cool word, it means to make an ester. And up to this point, we've talked about making an ester through the reaction of a carboxylic acid and an alcohol. But the truth is, due to the highly reversible nature of that reaction, sometimes it's easier to use a relative of carboxylic acid. So sometimes they're known as carboxylic acid derivatives. They derived, or they're the ugly cousins of carboxylic acids. So those are the carboxylic acid chlorides and carboxylic acid anhydride. So let's take a look at what those two organic families look like. So here's the general formula for each. I feel like the carboxylic acid is the most intuitive. Instead, it essentially looks a lot like a carboxylic acid, but instead of a hydroxyl group, we have a chlorine atom instead, and so that's thus the chloride name. The carboxylic acid anhydride usually causes students a little bit more trouble. Often is symmetrical on the two sides, but doesn't have to be. So anhydride means without water. And that, I think, can kind of help us with the structure, understanding the structure. So imagine you had two carboxylic acids up here next to each other. Got my carbonyl group and then my generic R. So if I chemically react them so that they are without water, so that I lose that water molecule between them and they bond then directly together, I get this structure where the oxygen ends up being in between them. And that is, the simple version of how they're formed. So they are two carboxylic acids, but without water. And that might help. Now the book does cover this, but I want to really make sure it's clear. We will not be including naming of these or the preparation, their synthesis. So make sure to always keep an eye on your objectives for the course so that you know what you're expected to be able to do on an assessment. So you are going to need to be able to recognize these and use these, but we're not going to bother with the naming and the synthesis. We just have enough to cover already. So let's look then at what that reaction looks like. So we can use a carboxylic acid chloride or a carboxylic acid anhydride to make an ester in a very similar way that we can use a carboxylic acid to. So let's look at those two reactions. So here I have generic formulas for those two kinds of esterification reactions. One, you'll notice that we aren't using that reversible arrow because in this case, the equilibrium favors the product quite a bit more than it does with the carboxylic acid. Now, notice the similarity in that we both create a carboxylic acid. Overall, there's a pretty similar thing that goes on to what we see with, ester, carboxylic ester. What we see goes on to when we use a carboxylic acid. We are going to take the alkoxy portion of the alcohol. The alcohol is going to lose its hydrogen. We're going to take off the chlorine in the same way that we would have removed, and that generates this product. So you'll see we make hydrogen chloride or aqueous hydrochloric acid. And we're going to then, now that we have this opening, getting rid of this, we have an opening for these to bond, and then we get an ester linkage then between the two. And then matter can't be created or destroyed, so we do have this product. Sometimes we do still end up focusing on the organic one though. Now, I think the reaction with the acid anhydride looks a little scarier, but it really comes down to the same thing. We're going to lose the hydrogen off the alcohol. It's going to go. The alkoxy group is going to be critical in making the ester linkage. So think about where an ester linkage needs to be made. It has to go to the carbonyl carbon. What that means, we actually have to lose a much larger structure of our acid anhydride. We have to lose this whole half so that our alkoxy group can come and the oxygen can bond directly to the carbon. And that's how we get this ester. Well, we got a lot more to take care of here, a bigger product. But if this hydrogen comes and bonds with this product right here, what do we end up getting? We get a carboxylic acid. So again, remember how I was like, these are derived from two carboxylic acids? It's two carboxylic acids, but without water. One of the carboxylic acids goes to make the ester. So one makes ester. And then the other is a product. And it grabs that hydrogen. It's just an extra product. They're both products. But it's going to be in its carboxylic acid form because it's going to pick up that hydrogen along the way. So let's look at some practice problems. As always, I'd encourage you to pause the video and see what you can do on your own. So we're reacting acetyl chloride, again, you don't need to worry about knowing how to name them, with ethyl alcohol, IUPAC name ethanol. So I want to react these two together. Sometimes I like to just like either cross them out because I know they're leaving, or you know, X them out but put them up here. This goes and this goes. This just helps my brain kind of really visualize what's happening. That leaves this left over with this little empty bond here. Oh no, I'm lonely. And this, we've lost a bond here, well, or this one. And so we're going to get a bond in between. So when I go to make my ester, a lot of the molecule is really unaffected by the chemistry here. It's just there at that carbonyl portion that things get exciting. Now I have an ester linkage to my product, and then I happen to have hydrogen chloride as a byproduct as well. You might want to use an opportunity like this to practice naming your esters. I can see from this that it would be ethyl ethanoate, or ethyl ethanoate, or if I wanted to go common, ethyl acetate. So here, what kind of molecule is this? This is an acid anhydride. So notice it is symmetrical in this case, and it's like it was made of two different carboxylic acids that reacted together without water. Do you recognize this structure? This is phenol. We learn about phenols as very separate from alcohols, especially because they are far more acidic, and so they kind of deserve to be in their own category. But phenol does in fact act like an alcohol as well, so our phenol is going to be our alcohol. I'm just going to put that there as a reminder. So it is behaving as our alcohol. So what's going to happen to it then? It's going to lose its hydrogen. Again, I like to kind of like, okay, so now I have a bond open. What is this going to lose? Well, what I like to do with acid anhydrides is I like to just find an ester linkage. Now, technically, they kind of have two ester linkage. There's not really two esters, but it's combined in a way where it's an ester on both sides. So it doesn't really matter which one. Maybe for, you know, I'm going to go here. Here's an ester linkage. So then I take the one with the oxygen, and that's the one that's going to leave and react with this hydrogen. So these two, it's going to go and grab that. So let's go ahead and write that product just so that we're done with it and out of the way. So the hydrogen that I'm writing here was from my phenol. The oxygen is from this half of my acid anhydride. And then I'm going to just draw the rest of that acid anhydride. And that is ethanoic acid. And like we said, when we do an esterification reaction with an acid anhydride, we make a carboxylic acid. So this is ethanoic acid, or acetic acid as it's commonly known as. Now my other product, I need to be making an ester, right? So my oxygen here is going to bond over here right there. So I have CH3 carbon double bonded to oxygen, and then I have my oxygen single bond, and then I'm going to include my benzene ring, which is what made it the phenol in the first place. I think earlier I referred to this as an ester linkage, and it's kind of a funny one because it's not quite an ester linkage because of the what's on this side. So I'm not sure that was appropriate language, but that is how I think of it and how I find it to divide the molecule in the two halves. And if I were going to name this, I would name this phenyl, not the same as it was up here. Notice that difference. Phenyl, and then either ethanoate, same as that we had up here, or acetate if I wanted to go common. Let's go ahead and stay. And finally, write the reaction for the preparation of ethyl propanoate from an acid anhydride. So there's some key words in this practice problem. So we have from. So from means that this needs to be my reactant. I like to kind of remind myself as I work. I'd encourage you to interact with your practice as much as you can. And prepare of, so preparation of, this means this is my product. And that even just tells me what side of the yield arrow I need to put things. So I'm going to be drawn way over here. Let's draw ethyl propanoate. So ethyl, that's 2 carbons, right? So we'll do line formulas because we've been focusing so much on structural and condensed. So that's 1, whoops, 2. I'm going to put dots just to make sure. So there's my ethyl, except really, because of this O8, that tells me something really important. It tells me that this ethyl group is also bonded, single bonded to an oxygen. And that oxygen is then bonded to this propanoate. So I guess I was doing line formulas. You know what? I'm gonna identify that one. So 1, 2, 3, 4. 1, 2, 3, 4. Now I know I have 1 carbon that I'm showing, but I just like to do that with our esters and things just because I don't know, I just like identifying that carbon. But I do want to make sure that I've counted it. So 1, 2, 3, 4. So there we go. So what would my reactants be? Because again, I'm wanting to prepare it, and I want one of them to be an acid anhydride. Well, I know that esters are made from an alcohol and an acid anhydride or an acid chloride or sometimes even a carboxylic acid. So let's start with the alcohol portion. The alcohol portion would come from here. Would generate this. So I don't like ethanol as a line formula. It's just weird. So I can see I have a 2 carbon. So I'm going to do CH2, CH3, and there's OH, or if, technically I could do that as the line formula. And that takes care of this portion of the molecule. Now I want this other reactant to be an acid anhydride. So I'm going to put that oxygen in the middle that I see. And then I'm going to 1, 2, 3, 4. So 1, 2, 3, 4. Double bonded to an oxygen. I'm going to assume it's a symmetrical one because it doesn't show me what the other product is. Or it didn't imply 1, 2, 3, 4. And then of course that actually does remind me that I do need another product to account for this other half. So I need a carboxylic acid as well. You can see I'm mixing up all my kinds of formulas. So this acid anhydride could react with ethanol to make this particular ester, ethyl propanoate, and this which would be 1, 2, 3, 4, propanoic acid. So let's just really briefly review the 3 different reactions that we've learned for making an ester. We have a carboxylic acid can react with an alcohol. It's highly reversible. And we make a carboxylic acid and water, and the water is generated from right here. We can use an acid chloride and an alcohol to make an ester, and we generate hydrogen chloride, which comes from right here. We can use an acid anhydride and an alcohol to make a carboxylic ester, or really we can just say an ester, and also a carboxylic acid. And the carboxylic acid comes from right here. You can see these are the pathways to get us to that reactant. So I want you to notice some similarities and differences between these. So similarities, switch colors, alcohol, alcohol, alcohol. That's a similarity across all of them. So no matter whether you're using any of these, the other reactant, is always going to be an alcohol. We always generate an ester, right? Ester, ester, ester. So we're going to look for that ester functional group. And our difference comes down a lot to then that other product. And that's just because of what reactant we're using. There we go.